Okay, so welcome to multivariable calculus math 150. This is going to be lecture 8. Actually, I think I'm off by a day here. And so what we're going to be doing today is we are going to be doing coordinate systems and level sets. So there is a lot of confusion I found over the years with level sets. So this is a really good lecture to be using computer animation as opposed to my drawing on a blackboard. And so I have set up in advance some mathematical code to just display things. I strongly urge you to learn how to use Mathematica. I've given you, I think, links. If not, I can resend them. It's about a 1 hour tutorial to just go through and learn the basic stuffs. It has some wonderful functions, which we'll see later today, called manipulate, which allows you to actually move things in real time. Coordinate systems. For some of them, it's going to be impossible for me to hide. The three big ones are polar, cylindrical, and spherical. When do you think you might use spherical coordinates? When dealing with a sphere. This is like a politician, when they're giving a speech saying, I love, whatever city, whatever state I'm in, whatever local town, this is the softball question. When would you use cylindrical coordinates? When you have a cylinder. When would you use polar coordinates? Yeah, that one's a little harder. Yes. When you have a circle, right? So there's a little bit of thought that is required. But for 2 out of the 3, it's really hard to hide when you would use that. Consider a sphere of radius 5. Okay. I probably want to use spherical coordinates for this one. Right. So there are lots of interesting units that you can use. And one of the whole purposes of this is to try to find a good system of units to use to make measurements. So some of my favorites, and you can look them up, are the Bruno, and this is well before the movie Encanto, the Helen, the millihelen, the Smoot. A lot of times the natural unit you use is not necessarily appropriate. Who here knows their units of measurement well? What's the unit of mass in the metric system? Gram, or actually I think it's the kilogram, because I think we usually use the MKS, but there's also the CGS, so gram is absolutely acceptable. What is it in the English system? I don't think it's the stone. I think a stone is 20 pounds, which would be a force. I think it's the slug. I didn't check this before class. I was hoping someone would know. It might be the slug, is the unit of mass. The MKS unit for magnetic measurement of magnetic induction is the Tesla, which is just not practical for everyday stuff on Earth. So, typical refrigerator magnet would be 50 Gauss. 1 Gauss is 1/10,000th of a Tesla. And so if you're measuring things in Tesla on the surface of the Earth, it's just not a good scale to study. So you ever want to figure out what is the right scale to study something? Anybody know how far 25 trillion miles is?
1 light year.
Very good. You're not exactly right, but you're ballpark. And when you're talking about astronomical distances, if you're within a factor of 10, that's not so bad. So the Earth's radius, you should know stuff like this. It's about 4,000 miles. Distance from the Earth to the Moon, 240,000. Distance from the Sun to the Earth is about 93 million miles. Does anybody know other units we typically use for these distances?
Like astronomical unit.
So the Earth is one astronomical unit. But there's another unit of measurement that we use rather than miles for distance.
Megasmoot?
No, we would never. I love the idea of a megasmoot, but you would never use a megasmoot on an astronomical scale. It would still be too small for this. So imagine you wanted to communicate with the moon. Are there any issues with communicating with the moon?
If distance isn't always constant in certain spots.
Right, it's approximately. But what will happen if you try to communicate with somebody on the moon? What will you notice? Then we really don't have anybody on the moon right now to do this, but what if somebody were on the moon? Would you have instantaneous communication? No. Why? It takes time. But how long does it take a signal to get from the Earth to the moon? So that's a good unit of measurement. It's about 1.25 light seconds. The Earth is about 8.3 light minutes from the sun. So, trigger, it is possible that the sun exploded about 6-7 minutes ago and we're all about to die. We'll know for sure in a few minutes. So, But if the sun were to explode, it would take a bit of time for that consequence to propagate and hit us. So a good unit of measurement is time for something like this, rather than, how long would it take light to travel that distance? Because light speed is constant. So Alpha Centauri, the second closest sun to the Earth, what's the closest? So Alpha Centauri is the second closest star to the Earth. What's the closest? The sun, right? Second closest is Alpha Centauri. It's about 4.3 light years away. And so that's a good way to put 25 trillion miles in context. Cultural extra credit. It's the ship that made the Kessel run in less than 12 parsecs. Yes. Millennium Falcon. Okay. Why is this such a bad line? Parsecs is a unit of space. So normally when you do races, everybody goes, the same course. So what was the justification in a later movie for this?
Well, the Kessel Run was weird, like cloud of nonsense. They took a shortcut.
Right. So the ship was able to take a shortcut that most people couldn't do, and that's why they did it in just 12 parsecs. They had to put that line in because they did not understand that, in an earlier movie when they were doing this line, they were meant to talk about how quickly did it do it, and just used the wrong thing. So cultural extra credit, well done on that. Okay. So, very maneuverable. All right. What are these two pictures of? Boston and Manhattan. And this is one of the only acceptable ways to say New York is better than Boston. Right? When you look at the grid system, in the Manhattan part of New York City, it is actually extremely easy to figure out where you are, to figure out how you want to get from one place to the other. This is just a semi-random snapshot of part of Boston and what the roads look like. Now, New York does have parts that look like this as well, but this shows you the benefits of a natural coordinate system. So for something like this, it's very easy to specify where you are, your north, south, your east, west. And if we wanted to go 3 dimensions, up, down, that wouldn't be that hard to do. Okay. When Neil Armstrong and Buzz Aldrin were getting ready for the historic first landing on the moon, one of the issues was trying to figure out just how far above the moon's surface are they. Well, one of the ways you often do this is you send pings down and see how long it takes to come up. But the way the ship was rotated, the pings were going off to the side, and so it didn't work. And so the way they were actually figuring out their height above the moon's surface is they looked at a little point on the ground and they saw how long it was taking that to move from like one part of the window to the other. And then they used very simple formulas to convert that to what must the altitude be for it to take this long to do this travel, because we know what our speed is. So really simple equations, coming into play in figuring out how high are we. And again, very natural to use coordinate systems related to a sphere in that case. All right. So what I want to do is I want to talk a little bit about polar coordinates. So essentially what's going on is, I have, a circle here. Here's the x-axis, here's the y-axis, and I give you some point over here. Here's the theta, this is all being drawn over here. Here is cosine theta, sine theta. And so given a point, I can represent that point 2 different ways. One is my east-west and north-south, and the other is how far from the origin, and then what angle am I making from the x-axis. So for a lot of problems, we can write our function as a function of 2 variables, x and y, or we can write it as a function of 2 variables, r and theta. For many functions, the function only depends on how far you are from the origin, not on your angle. Can anybody give me a force that only depends on your distance from the origin and not on the angle? any force that depends only on your distance from, say, the source, not on your angle. Gravity, G is, the gravitational force is the constant G, product of the masses divided by the square of the distance separating. So when you're trying to figure out the effects of gravity, it might be more convenient to use a polar coordinate system or a spherical coordinate system. So what we want to do, it's almost like currency conversion. We want to convert from Cartesian to polar. So if I give you x and y, it's, okay, x is r cosine theta, y equals r sine theta. So if I give you r and theta, it's very easy to get x and y. What if I give you x and y? How do I get r and theta? So can somebody tell me how to get r if I know x and y? Yes. Okay, and so what would that be? Good. So r is the square root of x squared plus y squared. And this is by Pythagoras. And so r is going to be greater than or equal to 0. So it's always important to know where are things defined. The radius is defined as a non-negative number. It's how far are we from the origin. Okay, what about theta? You have two choices. One is common, one is uncommon.
The tangent relationship.
Yes, and so you could say y over x is the tangent of theta, right? So theta is arctangent of y over x. And 0 less than or equal to theta less than 2 pi. You could use, of course, instead of arctangent, you could use what could you use instead of arctangent? If you didn't, yes. Well, okay, tan inverse is the same as arctangent. But instead of using tangent, you could use so right, but I mean, we're given x and y, so we would really, I mean, you could of course use arc cosine as well, yes. And you could say, well, theta is arc cosine of x over r, which is x over the square root of x squared plus y squared. You could absolutely do that. So you could use arc cosine, you could use arc sine, you could use arc cotangent. Most people use arctangent. So when you have a coordinate system, you want to make sure things are nice. If I give you x and y, I can get r theta. If I give you r theta, I can get x, y. Is it always 1-to-1? Do I ever have to worry that there might be more than one way of writing something? Does every point, r theta give you a unique x, y? Can different pairs of r theta give you the same x, y?
If you did like negative r and then you did
We can't do negative r,
no.
because remember, we're saying r has to be greater than or equal to 0.
Oh,
So we're not allowing, so if you could have negative r, then you could have multiple representations, yes.
okay, you could do pi minus theta. Then I guess that's a lot.
Right, that'd be a different point. So there is a place where you have more than one way of writing something. Where, yes. Yeah. If r equals 0 and theta anything, you get 0, 0. So there's one point where you don't quite have a 1-to-1 relationship. There's one point where multiple choices of r theta give you the same point in x, y. So if I'm at the origin, how do I write myself? My r is definitely 0, but my angle can be anything. That's one point. So the hope is that there's one point where the transformation breaks down a little bit, maybe it's going to break down in such a way that it's not so bad. If you integrate the function 1 over square root of x from 0 to 1, the function is blowing up at the origin, but the antiderivative of 1 over square root of x is 1/2 x to the 1/2. That's actually integrable. So even though it blows up so slowly that everything is okay. We're going to just hope things are fine over here. All right. Any questions about polar coordinates? Okay. Cylindrical coordinates is basically polar with z equals z along for the ride. So when you're doing cylindrical coordinates, it looks an awful lot like polar coordinates. You just have z equals z. So it's basically just dropping a circle. A circle is just sweeping out a cylinder in space. And so over here, the website I was pulling it from is writing tangent inverse. You can also write it as arctangent of y over x. Either is fine. And again, it's just worth noting, r is greater than or equal to 0, 0 less than or equal to theta, say less than 2 pi. So this is cylindrical coordinates. Okay. The last one, any questions? Basically, you can just polar with z. The last one is spherical. And this is where things are a little bit bad. So I was pulling this from Wikipedia. I'm going to change their r to a rho. And so there are a couple of different conventions that people can use. You can use r or rho for the radius of the sphere. And then you can either have theta or phi as the angle coming down from the z-axis. Is there anybody here who is taking a physics class or has taken a physics class at Williams? Okay, have you done spherical coordinates? I believe the physicists like to have theta as the angle coming down from the z-axis. And as I've remarked to some of you, I first saw spherical coordinates in the physics department as an undergraduate. And so I always have to fight my instinct to have theta coming down from the z-axis. In mathematics, we like to have theta being in the xy plane. And the reason is, if we do it that way, it's basically just polar coordinates now bumped up to a sphere. And so let's try to think of what's going on. So the first is I have some angle phi coming down from the z-axis. I will put this on Zoom so that people can see it at home. I forgot the basketball in my office, so I will just, Boy Scouts, try to do something similar. All right. Do we accept this as an approximation to a sphere? So you start off at the North Pole and you come down. And how far you come down is your angle phi. Do you want phi to go all the way from 0 to 2 pi? Which means you come back to where you started. Or do you want to just go from 0 to pi? If we only go from 0 to pi, once we come down here, if theta then goes from 0 to 2 pi, we spin all the way around. So we can get to every point by having phi just go from 0 all the way down to pi. And then once we go down a certain amount, then we spin all the way around. And that gives us everything. So you don't need theta and phi to go all the way from 0 to 2 pi for each. That would actually have you covering the sphere twice. And so that is why in the coordinate systems we use, we typically only have phi go from 0 to pi. So over here, I would be very explicit and I would say, phi goes from 0 to pi, or 0 less than or equal to phi less than or equal to pi. And then theta goes from 0 to 2 pi, or 0 less than or equal to theta less than 2 pi. And then rho will be greater than or equal to 0. So when you look at what's going on, you start off by coming down rho from the z-axis. And then you spin around in the parallel to the xy plane. Okay. So let me take this to the next slide. Okay. So let's look at what's going on. So we're at this point over here, and we're spinning, in a circle above the XY plane. How high is it above the XY plane? Well, let's try to draw things. So here is the Z-axis. Here's the XY plane. And now let's say, here I am coming down like this. Here's my angle phi. This vector has length rho. So what is this length going to be over here? So I've got my height. And I'm going to call this the radius of the circle that's parallel to the XY plane. So what's the height h? That's our z value. And if we go out rho and we're coming down phi, we have a triangle. So what's the length of the side that's next to phi?
Rho cosine.
It's just going to be rho cosine phi. And if we go back a page, oh, good. Z equals rho cosine phi. Excellent. Well, if z is rho cosine phi, then this radius r is going to be what? So what will the radius r equal?
Rho sine.
It'll be rho sine phi. Now, feed into polar coordinates with r and theta, with theta, given, and r equals rho sine phi. So we know x is r cosine theta and y is r sine theta from polar coordinates. This is why mathematicians prefer to keep theta for the angle that's in turning parallel to the xy plane. And we like to use rho for the radius of the sphere, and we like to use r for how far we have walked from the z-axis parallel to the xy plane. Because now we can just use polar coordinates. Now we use r and theta. So we basically reduced the radius by a factor of sine phi, and we'll get x is r sine theta becomes rho sine phi cosine theta, and y is going to be rho sine phi sine theta, and from before, z was just equal to rho sine phi. And if we go back to what we had a moment ago, that is exactly what we had from before. So this is where spherical coordinates come from. Yes. Oh, good. That is a typo. Thank you. I copied the wrong thing. Thank you. Z is supposed to be cosine. Thank you. So this is where spherical coordinates come from. The most useful times for spherical coordinates are when you have something that doesn't depend on theta or phi, that only depends on the distance. And again, I can give you rho theta phi, or I can give you x, y, and z, and there are conversions between them. And so here are the conversions, and we like to use arc cosine. So it's nice that arc cosine gets into the game. So we have arc cosine and arc tangent. There's a couple of different ways you can do this. So if you think about something on the Earth's surface, how would you specify where you are on the Earth's surface? Longitude and latitude. And this is assuming that the Earth is a perfect sphere. Approximately. So if you assume the Earth is a perfect sphere, I don't really have to specify the radius because it's the same everywhere. If you start taking into account the fact that the Earth is not a perfect sphere, and there's many ways in which it's not a perfect sphere. Did I send you this article by Asimov, The Relativity of Wrong? All right, I will try to remember to send that later today. Great, great article. But if the Earth is a perfect sphere, I just have to give you latitude and longitude. Okay. Any questions on spherical coordinates? All right, so now what we're going to do is we're going to start talking about level sets and trying to find ways to visualize things. So we talked a little bit earlier about, if we are in Manhattan, we have the east-west, we have the north-south, and we can add another direction, up-down. Can anybody give me speak of the following famous movie line? He's intelligent, but inexperienced. His patterns indicate two-dimensional thinking. Yep. But who in Star Trek? Yes. Khan. So Khan was frozen in time and appears in Star Trek in the famous first season episode Space Seed and comes back for the second Star Trek movie. And when he's having the fights with the Enterprise, he's used to fighting on the Earth's surface. And so he's used to two-dimensional battles. And so the big thing is, let's go underneath. Works beautifully. We can discuss 2 dimensions, we can discuss 3 dimensions. But at some point, let's start discussing a 4-dimensional plot. Let's start discussing a 12-dimensional plot. How the hell do we handle something like that? So most of the math I'm going to teach you, you're never going to use. I've accepted that. One of the things you will use is data visualization. And how do you convey a complex object in a way that people can understand? Here's a really nice one. This is a map of average daily precipitation in the United States. And so basically how high up you are is a function of how much rain you're getting. Does this look reasonable to you? Okay, there should be certain areas of the country that you quickly check. What's one area that you quickly check? Yeah, New Mexico, Arizona. My parents retired to Tucson. And so, basically almost all the rainfall is the week we go to visit them. It's amazing how we seem to time that every year. Very little rain in the desert. Where in the US is it famous for raining? Oregon, Washington, Seattle, and you see, oh yeah, okay, I can see it down there. The Northeast, in fact, the whole East is definitely a lot more rainy. This map at least looks reasonable, quick view. Does this give you a good sense of what's going on? Can you look at this and get some idea of which parts of the country are getting how much rain? I think it does a decent job. The problem is this is not necessarily an easy map for you to make yourself. And as you go to higher and higher dimensions, it's going to get worse and worse. You sometimes see maps like this when they're talking about distribution of voters. That's a really good one where they often have, and you can tell where the cities are, for instance, in the United States very easily by looking at number of votes. Try to move on to the next slide. All right, so here is the definition of a level set. It seems like I just paused the screen share. Okay, so here's the definition of level set. So a level set of a real valued function f of n variables is the set of all inputs x1 through xn such that the output takes on a special certain value. So the level set of height c will denote an L sub c is all inputs such that f evaluates to c. You want to have good notation. For the derivative, we use f prime to denote that it is something related to the original function. For level sets, why do you think we use L sub c? Good, the sub c is telling us the height is c, and why do you think we use L? Yeah, level set, right? So you always want notation that you can just quickly glance down and see what's going on. So it's trying to find all the inputs that give you the same output. So does anybody know any famous level sets that you might have seen maps of? Weather. So what is the canonical example? So no, America has not fractured into several different nations. These are just where we have lines of the same temperature. Anybody know what they're called? You might have done this in a chemistry class. Isotherms, lines of constant temperature. Anybody know what a line of constant pressure is? If I really cared, I would have looked.
It's used to denote a low pressure system.
Yeah, and so what's a line of constant pressure called? I think it's isobar. But so, this is, I can just quickly look at this and I can get a rough sense. The weather should be continuous. You shouldn't go from 50 to 85 degrees, in a very small step. And so it makes sense that you're going to have a nice continuous plot. This is drawing all the points that have the same temperature. So you have over here the line of 55 degrees, 50 degrees, 60 degrees, 60. Makes sense. Okay, warmer as we go further to the south, closer to the equator. Makes sense as we go closer to the north. Okay. And of course, you'll have some exceptions where it's getting really cold, and you can ask what's going on over there. What other kinds of plots might you see of constant, of plots like this, where you have curves of constant value? Yes, and so hopefully that's the next one. Yes, excellent, that is the next one. I tried to find a good one of Mount Greylock, but I didn't find a contour map that I liked fairly quickly, and I didn't care enough to keep searching. So here on the left is a map of some mountain area, and you can just see how high things are, and so on lines of constant feet. So here looks like 50,000 feet here, 8,000 feet, 11,000 feet here. And then over here on the right, I believe it's the same region. If not, it's fine. It's got the three-dimensional plot over here, and then projecting downward. You can now just glance down and get a sense of what's going on.
Are those modeled using GIS?
I have absolutely no idea. I wouldn't be surprised. And if you go down to other parts of the science center, to the geophysics parts, you'll see lots of maps like this. All right. The three-dimensional one is very nice to look at, but because it's three-dimensional, you may not be able to see some features behind the mountain. And having a plot of what the values are, you can just glance down and see. How many people have seen the movie The Matrix? So at one point you have a famous line by Cypher who goes, after a while, I don't even see the code. I just interpret it as, and I can just see the people just by looking at the code. After a while, you can just look at this contour plot and get a sense of what kind of shape it is. Looking at this, okay, I'm probably getting either really high or really low at these 2 points. Oh, I see the values are going up, I'm getting really high. And so it allows you to convey a lot of information very quickly. The question becomes, how do you do these plots? Well, one thing is you can just take a bunch of random points and just plot their values and connect. Fortunately, there's also a lot of programs that do things for you. So Mathematica, contour plot gives you a plot, and it draws lines of constant value. And if you want, you can almost surely open this up and tell you how many things to do. I will try to switch now. And I will try to switch now to Mathematica. And I have taken screenshots of this, so this will all be in the notes as well. Okay, so here is the first plot. And if I put my cursor over here, it says the value here is 0.8, the value here is 0.6, the value here is 0.4. So that when I have this plotted over here, as I move this over, I can actually see what the value of the lines are. How else do you think I might be able to tell the value of these lines? What do you think Mathematica is trying to do to give me some sense? Yes. The coloring. So as the color is getting darker towards the blue, the value is getting lower. And so by having, you can have it display the color code, but by having things in a color code, you can just quickly glance at it and see what's going on. So always use color when you can. When you looked at the temperature maps, we had regions in different colors as well. And so this is a contour plot. And so does anybody know what object this looks like? Look at this. Plotting. Yes. It looks like, yeah. And so what do you think it might be? Possible. One of my favorite moments was we were looking at some of his work at Math Smoker, and we said, hey, that kind of looks like the Enterprise insignia. And so what do you think might be these concentric circles? These are heights of constant value. Can you think of any objects where the heights of a given value above the XY plane would be circles? That's a sphere. So this is not quite as, this is kind of a generalized sphere. So the one below, I've actually modified the function a little bit. And so my function is going to be, if x squared plus y squared is at most 1, the function is 1 minus x squared plus y squared. Otherwise, it's going to be 0. Yes. So it's not a sphere. If it was a sphere, instead of 1 minus x squared plus y squared, what should it be? Well, so if you have a sphere, x squared plus y squared is z squared. So z is the square root of 1 minus x squared plus y squared. This is just 1 minus x squared plus y squared. So this is not quite a sphere. And so I'll let you play with it. It does have a lot of symmetry. But this is telling you that you may not want to use spherical coordinates for this. This is probably going to be what coordinate system? Probably cylindrical. Now, what's nice is you can clearly see that if x squared plus y squared takes on the same value, then the height is going to be independent of where you actually are. All that matters is how far are you in the xy plane from the origin. So I know the level sets are going to look like circles. Let's do another one. So if I go down a little bit, I'm now plotting the sine of x squared plus y squared. So when you look at this, what do you think of when you see this? Are you sure? Yes. Okay, what is that?
Yes, I think it was 3D kind sort of function where high, not like lower is.
Okay, good. It's really like low points, up points. Do you think it's going to be periodic or not? We're plotting the sine of x squared plus y squared. Yeah, because sine is a periodic function. So all I really care about is what is x squared plus y squared up to, say, multiples of 2 pi. Does it matter what angle I am from the origin, or does it only matter how far I am from the origin? Yeah, it only matters how far, because it's just x squared plus y squared. So if I were to convert to polar, I don't know if I can write on this. Nope. If I were to just look at it like this, all that matters is x squared plus y squared. So if I convert to polar coordinates, it's just the sine of r squared. Now, if you want to actually try to get a sense of what this looks like, you could, of course, plot the three-dimensional function. And so what I'm doing here is I am plotting. So plot 3D, surprise, surprise, does a three-dimensional plot. And I'm having it plot 2 functions. I'm having it plot my function sine of x squared plus y squared. And I'm also having it plot the function c. C is a constant. And I'm using this beautiful command in Mathematica called manipulate. And outside, I'm having c range from -1.2 to 1.2. Well, what's the largest my function sine of x squared plus y squared could be? Where does sine of x squared plus y squared live? So where does the sine live? Yes. So it lives between -1 and 1. So if I go, c goes from -1.2 to 1.2, that's going to be more than enough to get everything. Here I'm plotting c equals -0.535. Let me just rerun the code. And so here we go. And we start off with the plane, c equals -1.2 below our function. And now as I raise it up, it's like the water is flooding. You can see where it intersects. And where it intersects over here, these are going to be the level set of that height c. It's all the points like that. And at some point, anybody know where it's going to get that little dip? What value of c? 0. So do you see the little dip in the center? Kind of hard to see. So let's make it 0.05, which is a very small amount. And now you can see, a little bit over the. I can, raise this a little bit more if I want. And you can now see that there's like a ring on the inside and a ring on the outside. What's nice is if you just click on the graph, you can actually just change the angles. If I go perfectly like this, you'll barely even see the plane. But if I start coming at angles, if I look straight down, you can see really what's going on. If I lower this, again, I want to come down like this, you can really see where it's hitting. So these are wonderful visualizations. The problem is, as we go further and further, we're going to have more variables than just 3. And so when you start trying to plot, something of 6, 7, 8 variables, it's extremely hard. So a lot of times what you do is you try to plot what are the key features. And maybe I'm a function of 6 variables, but I'm only going to plot the 2 or 3 that matter the most. Well, even plotting 3 variables is hard. So if you have 3 variables you care about, it would be a 4-dimensional object that you're now plotting, right? You give me 3 inputs and I give you an output. How can we plot something that's 4-dimensional? What you often do is you use color to indicate the value. And so you could do a 4-dimensional plot by just having your input is your standard x, y, z, and then the color you assign is going to be the value of the function. The problem, of course, is that you won't be able to see what's on the inside. So it becomes a tremendous challenge to figure out how do you actually display and evaluate stuff like this. All right, so this is just showing a bunch of plots. These are the ones we just did, just different snapshots. Okay, and so then the question becomes, if I give you a function, can you find the level set? And depending on what you have, different level sets will be easier to calculate than others. So let's say I give you maybe f of xy is the sine of 2x plus 3y. And I want to try to find the level sets. So I want to find the level set of height c for my function. So this is going to be the set of all x and y such that the sine of 2x plus 3y equals c. I claim some values of c are very easy to solve right now, that you can immediately tell me what the level set is. So can somebody give me a value of c where it's very easy to tell me what the level set is? Okay, I actually think 0 is a little bit hard, because you have to give me all x and y, such that the sine of 2x plus 3y equals 0. There's some points that are easier. Well, 1 is, I think, also still a little bit hard. Yes. I'm sorry? So you have to give me a value of c. What value of c are you giving me that's going to be very easy to determine all the x and y, such that the sine of 2x plus 3y equals c? So there are some values of c where it's going to be very easy to see which values of x and y could be.
Something's out of bounds.
Yeah, so give me a value of c. 2. So if the absolute value of c is greater than 1, then the level set of c, level set of height c, is the empty set. This is because -1 is less than or equal to the sine of any input is less than or equal to 1. So sine lives between -1 and 1. So if I give you a value of c equals -2 or 2022 or -5, there's going to be no input that works. Okay, now let's look at other values. So we need to study -1 less than or equal to c less than or equal to 1. And so we have f of xy is the sine of 2x plus 3y. And we'll have -1 less than equal to c less equal to 1. So let's say the sine of 2x plus 3y equals c. What does that mean? So if the sine of 2x plus 3y equals c, what do you know about 2x plus 3y? So let's take a specific example. Let's say we want the sine of 2x plus 3y equals 1. When is the sine equal to 1? Anything else? So when else could it be? Pi over 2 minus 2 pi dot dot dot. So it's actually going to be 2x plus 3y equals pi over 2 plus n 2 pi for n an integer. So you're going to have lines. So you would get y is equal to negative 2/3 x plus 1/3 pi halves plus 2 pi. I've done the effort. So you're going to get a bunch of lines where the function will take on the value 1. More generally, if I say the sine of 2x plus 3y equals c, what must 2x plus 3y equal? So if the sine of 2x plus 3y equals c, how would I figure out what 2x plus 3y is? What function would I use? We would use arcsine. So 2x plus 3y is arcsine of c. And we have to be careful because there's going to be more than one choice. Right? If something works, we can add 2 pi or 4 pi or 6 pi, or subtract 2 pi or 4 pi or 6 pi. And so you would basically get lines. So you would have lines where it's constant. So we already know that it should look like a bunch of lines. So if I now go back to Mathematica, and let's do plot sine plus 3y. Let's go from negative 10 to y equals to negative 10. So not surprisingly, it does look like lines. And cut and paste is absolutely wonderful. Instead of contour plot, let's do plot 3D. Here is my function. I'm plotting it over such a large range, it's kind of hard to see. Let's just do maybe -1 to 1. Oops. And let's do that for y as well. Maybe I want to go a little bit further. Maybe I'll do -2. You start to really see, and you can really play the games by rotating this to try to get a sense of what's going on. If I wanted to try to find level sets, I'll just put in a manipulate. And then because I want to plot two functions, I put curly braces, and then I put the function in the curly braces. And then I'll have and now you can see what happens as I raise my c to different heights. If I click the plus sign over here, I can see the value. I can put it in at 0. And these lines over here now, those are going to be corresponding to 0. If I wanted to see what's going on at 1, it's just touching now. So it's kind of hard to see. So maybe instead of doing 1, maybe if I do 9, 8. That's a little bit easier to see now. It's lying a little bit. Yes.
If a plane of one, that'd be a tangent plane.
It would be a tangent plane, exactly. I would just barely hit it everywhere. But it's kind of hard to see because it's just hitting. So if I do 0.98, that's pretty close. And if I do 0.999, at this point, I'm not able to see it anymore. So this is sometimes where you just have to play games with the computer system so that you can see what's going on. All right, this is a good place to stop. Have a great rest of the day, and I will see you on Friday.